Let's talk about the delta ratio, also known as the gap ratio. Before we begin, we have all seen this table, right? For all kind of acid-base disorders on an ABG, we check for the compensation, right? Let's take the first example. For metabolic acidosis, we check for the expected PaCO2, right? Now, if my patient's PaCO2 is higher than the expected PaCO2, what does that mean? It means my patient has some extra CO2, an extra respiratory acid. So, my patient has a respiratory acidosis in addition to the primary metabolic acidosis, right? Therefore, for a metabolic acidosis, the compensation rule helped me find out if there was any additional respiratory disorder, right? Similarly, in a patient with a primary high anion gap metabolic acidosis, a delta ratio is used to find out if there is any additional metabolic disorder. So the PaCO2 gave me if there is any additional respiratory disorder, and the delta ratio gives me if there is any additional metabolic disorder in case of a primary HAGMA. So what can be the scenarios? They can be a pure HAGMA, no other additional metabolic disorders, right? There can be a HAGMA plus a non-anion gap metabolic acidosis, a NAGMA, or there can be a HAGMA plus a metabolic alkalosis, right? So the delta ratio values will come to the ratio in a bit. The values will be in pure HAGMA, it's going to be 1 to 2. In HAGMA plus NAGMA, it's less than 1. And in HAGMA plus metabolic alkalosis, it's more than 2. Now let's come to how these values were derived one by one. Before that, what is this ratio? Delta ratio. Delta means change. So it's a ratio of two changes. The change in anion gap by the change in bicarbonate. The delta anion gap by delta bicarbonate. The delta anion gap is the measured anion gap in the patient minus 12, and the delta bicarbonate is 24 minus the measured bicarbonate in the patient, right? So let's come to our scenarios one by one. What was my first scenario? That my patient has a pure HAGMA, right? Here there are going to be some acids, yes, and this acid is going to dissociate into H plus some acid anions, right? Now this H plus is going to go and bind with bicarbonate to form carbonic acid, right? So can we say that for each acid anion being produced, one bicarbonate keeps getting used up? Yes. And it is this acid anion that drives the change in the anion gap, because this is an unmeasured anion, right? So can we say here the delta anion gap is the same as the delta bicarbonate? Yes. So what's my delta ratio here? It's the delta anion gap by delta bicarbonate. Since the numerator and the denominator are the same, it's 1. It's actually 1 to 2, and I'll tell you why. Let's put in some numbers. Let's say there were 5 acid molecules. Now these dissociate into 5 H pluses and 5 acid anions. Now these acid anions are all staying in the blood. They're not going anywhere else. But out of these 5 H pluses, 2 are going intracellularly and 3 are remaining in the blood and bind 3 bicarbonates to form 3 carbonic acids. So for 5 acid anions, 3 bicarbonates are getting used up. Therefore, the numerator or the delta anion gap can be slightly higher than the denominator or the delta bicarbonate. That is why the ratio can be slightly more than 1, but only up to 2, not more than that. So if my ratio is 1 to 2, I can say that my patient has a pure HAGMA, right? Let's come to the next scenario, which was patient has HAGMA plus a NAGMA, right? So for HAGMA, there is going to be some change in anion gap. We saw it just now. And there is going to be some change in bicarbonate, right? In NAGMA, there is no change in any anion gap. It's evident from the name itself, non-anion gap metabolic acidosis. But there's going to be a change in bicarbonate here as well. Here, can we say that the delta anion gap is less than the delta bicarbonate? Yes, because the delta, I'm sorry, here it's going to be no. The delta anion gap is only being brought about by the HAGMA, but the delta bicarbonate is being brought about both by HAGMA and NAGMA. So what's my ratio here? The delta ratio is again the delta anion gap by delta bicarbonate. Since the numerator is less than the denominator, the ratio is less than 1, right? Let's come to the last scenario, which was that my patient has HAGMA plus a metabolic alkalosis, right? So for HAGMA, there's going to be some change in anion gap. There's going to be an increase, right? And there's going to be some change in the bicarbonate. Since this is a metabolic acidosis, there's going to be a decrease, right? In metabolic alkalosis, there are no unmeasured anions being produced, so there is no question of any anion gap change. But there's going to be some change in bicarbonate. Since this is a metabolic alkalosis, there's going to be an increase, right? Now, the primary disorder in our patient is what? A HAGMA, a metabolic acidosis. So, the net result has to be a metabolic acidosis or a decrease in bicarbonate. So, can we say that the decrease in bicarbonate produced by the HAGMA is more than the increase in bicarbonate produced by the metabolic alkalosis? Yes. Let's put in some numbers. Let's say there was 6 change of anion gap for the HAGMA and 6 decrease in bicarbonate due to HAGMA. And for the metabolic alkalosis, there was a 4 increase in the bicarbonate. So, what's the net change in bicarbonate? 6 minus 4 is 2. There's a decrease. The decrease is higher. There's a change in a decrease of 2 bicarbonates for what? For a 6 increase in anion gap, right? So, the delta anion gap is clearly greater than that of the delta bicarbonate. Yes. So, what's my delta ratio here? As the numerator is significantly higher than the denominator, the ratio is 2, right? So, for a ratio of 1 to 2, I have a pure HAGMA. If the ratio is less than 1, I have a HAGMA plus NAGMA. And if the ratio is more than 2, I have HAGMA plus metabolic alkalosis. So I hope this is clear.